Hello guys, in this video we're going to look at characteristic equations of circles, how to obtain the characteristic equation of a circle, because this is quite important before we go about studying the Argand diagram under complex numbers. So when the problems you would get under complex numbers would be to uh, draw diagrams in the complex plane. So uh, one of these diagrams would be circles. So for that you need to have a basic understanding of a circle and what is the characteristic equation of the circle would look like. Okay, so what is a circle? How do you define a circle? Circle is defined as a point traveling at a constant distance away from a fixed point. It is a point traveling at a constant distance away from a fixed point. So that is the path of a circle, or the locus of a circle. We call that the locus of a circle. You can see here that this point, wherever it is, it will always be at a constant distance away from a fixed point. So in this case, so this does not look like a circle, but this is a circle, and this is called, the fixed point is called the center of a circle. Okay, fixed point is called the center of a circle. So we're gonna get our characteristic equation based on this logic. Let's look at circles in a Cartesian plane. So in a Cartesian plane, you have y-axis and x-axis. So any point in this plane can be represented by a coordinate between x and y. So this is a general representation of a point. Every point is unique. Every point will have a x coordinate and a y coordinate, right? So what is meant by the characteristic equation of a circle? In Cartesian plane, you can sketch circles. So when you sketch a circle, there will be a center for that circle, and the points on this circle can be represented by a certain coordinate, a variable coordinate. So the characteristic equation of a circle in this case should be able to represent all the coordinates which falls upon this circle, all the coordinates which falls upon this circle, and not any other coordinates. So other coordinates shall not be included in that characteristic equation. So this is the basic idea. So we'll look at a special case first. We'll look at a circle whose center is at the origin, right? We'll look at a circle whose center is at the origin. Okay, so this is the origin, 0, 0. We'll look at a circle whose radius is r. So if the radius is r, this would be the path of a circle, or just a circle. You can call it a circle, right? So in this path, there will be certain coordinates which fall upon this path, and the rest of the coordinates in this plane will not fall upon this path. Okay, so the logic behind obtaining the characteristic equation is that the point, whatever the point you choose, let's say this point is x comma y, this point should always be at a constant distance away from the origin. That is the logic. So in a Cartesian plane, you know how to obtain the distance between two coordinates point. So the distance, we'll call it the distance, is obtained by uh, difference in x coordinate, difference in x coordinates. So I'm looking at these two coordinate, difference in x coordinate square plus difference in y coordinate square. This should be equal to the distance square. Distance square, distance is r, now it should be square. So we can simplify this more. We'll get x squared plus y squared minus r squared is equal to 0. So I'm just going to take r squared onto the other side, because you know that mostly the equations you study in this course will have this form. There will be an expression, the expression is equal to 0, right? Now this is the characteristic equation of a circle pertaining to a center which is located at the origin of a Cartesian plane, and the radius is r, right? So this equation will reveal us all the xy coordinates which fall upon this circle. Okay, so this is the most simplest case that you will see, and in the next video we'll look at a more general form.